Today, we are diving into the absolutely amazing world of biomaterials. We're talking about the incredible stuff that's engineered to work inside our very own bodies. Think about the pin that holds a broken bone together, or the valve that keeps a heart beating. This is where high-tech engineering crashes right into human biology. And honestly, the results are pretty close to magic. And let's be real, this question gets personal, and it gets personal fast. I mean, most of us know someone with a pin in their leg, or a new hip, maybe a stent in their heart, and those things, they're not just random bits of metal and plastic. Oh no. They are meticulously designed, high-performance materials, built for what is probably one of the toughest jobs you can imagine, functioning inside you. So, what does it actually take for a material to make the cut? Well, first and foremost, it has to survive. And it has to survive in one of the most hostile environments we know of. Right. This is the number one challenge. Just think about what happens when you leave a piece of metal out in the rain, right? It rusts, it degrades, it falls apart. Now imagine that same process happening 24/7 for years on end, but inside a warm, salty, fluid-filled machine. That's our body. It's basically a constant chemical attack. So any material we put in there has to be unbelievably tough just to last. And the jobs these materials do are just so incredibly diverse. I mean, they can replace an entire joint, like a hip, or they can help you heal, like the stitches that pull a wound together. They can improve how your body works, think of a pacemaker keeping a heart in rhythm, or they can even help doctors figure out what's wrong in the first place, like with probes and catheters. The range is just, it's mind-blowing. So, to tackle all these different problems, engineers basically have four main families of materials in their toolkit. Let's get to know the key players, shall we? Okay, first, a really important point of clarification. When we say biomaterial, what we're talking about is a non-living synthetic thing, like a piece of titanium or a special kind of plastic that's made to go into the body. This is completely different from a biological material, which is the stuff your body makes itself, like your skin or your bones. It's a super important difference. So here they are, our four families. First up, you've got polymers. Think of them as specialized plastics. They're resilient, easy to make into different shapes, but they're not super strong. Then you have the heavy hitters, metals. They're strong, they're tough, they're ductile, which means they can bend a bit without snapping, but they can corrode. Next are ceramics. These are amazing because they're super biocompatible. The body pretty much ignores them. The downside? They can be brittle. And finally, you have composites, which try to mix and match to get the best of all worlds, but they can be a real headache to make. Each one has its own special job. Now, the idea of putting spare parts inside a person isn't actually new, but being able to do it successfully, that's a surprisingly recent thing. And a quick peek at the history shows some really fascinating turning points. So get this, the biggest breakthrough on this entire timeline wasn't even a material. It was a procedure. Back in the 1860s, Dr. Joseph Lister introduced the whole concept of sterile or aseptic surgery. Before him, almost every implant surgery failed because of infection. He made the whole field possible. After that, the materials themselves started to catch up. We got better steel in the 20s, then a biocompatible plastic that was discovered by accident from injuries to WW2 pilots in the 40s, and finally the first bone cement in the 50s. Okay, for the rest of our time, we're going to zoom in and focus on just one of these families, the mighty metals. When it comes to any implant that has to carry a heavy load, these guys are the undisputed champions. In the world of implant metals, you've got two classic choices. On one side, you have 316L stainless steel. It's strong, it resists corrosion pretty well, and it's perfect for temporary things, like the plates and screws used to hold a broken bone together while it heals. But for a permanent high-stress job, like a total hip replacement that has to last a lifetime, you need something tougher. And that's where cobalt chromium alloys come in. They are just superior when it comes to strength and resisting wear and tear. But what if you need the absolute best, the top of the line? Well, for that, engineers looked up to the sky. They borrowed a wonder material from the aerospace industry, a material famous for being both unbelievably strong and ridiculously light: titanium. And this chart right here shows you exactly why. It's a look at the strength to weight ratio. So you see stainless steel and cobalt chromium. They're solid, right? Good performers. But then just look at the titanium alloy. I mean, it's not even in the same league. It delivers an incredible amount of strength for its weight, which is precisely what you want for something that's going to become a part of your own skeleton. But that's not all. Titanium has another trick up its sleeve. And this is where we really start to see the future of biomaterials. The whole way of thinking has shifted. See, it's no longer good enough for the body to just tolerate an implant. The new goal is for the body to actually accept it, to make it a part of itself. And this is how it works. It's a process called osseointegration. What happens is titanium just naturally forms this very stable, super thin layer of oxide on its surface. And for reasons we're still figuring out, our bone cells love this surface. They don't just put up with it, they actively grow onto it and bond directly with it. The implant literally becomes fused into your bone. It's incredible. So, we've got strong metals, we have metals the body can bond with, but what if we could take it even one step further? What if a metal could be programmed? What if it could have a memory? And this is where we get into some truly mind-bending science. Take a look at this chart. That top line shows a normal steel spring. You stretch it too far, and that's it. It's permanently bent out of shape. But the bottom line? That's a titanium nickel alloy, or TiNi. You can deform it, and it just snaps right back to its original shape. This property is called superelasticity, and it's what makes shape memory alloys so special. It's why they're used for things like braces. The arch wire applies this constant, gentle force to move your teeth, something a normal wire just can't do. You know, after all of this incredible engineering, from fighting corrosion to building strength to even having a memory, it all comes down to one simple, powerful word: biocompatibility. This is it. This is the ultimate goal. It just means the body accepts the implant without getting irritated, without inflammation, without any bad reaction at all. It's the simple, elegant peak of a huge mountain of complex science. We've come so far. We've created materials the body basically sees as its own. But that just leads to one final, really exciting question. What happens next? What happens when we create materials the body can actually learn from? When we move from just replacing tissue to creating materials that can signal our bodies to regenerate and heal themselves? That, right there, is the next frontier. And it's happening right now.